how do I approach this? I always make a little sketch of what is going on, which is I refer to as a template. I've explained this in other videos, so check out those in the link below. But I will go through it again here today. So it says aqueous potassium manganate in acidic conditions can be used in analysis. A student analyzes a sample of sodium sulfite using the following method. The student dissolves 0.72 grams of impure sodium sulfite in water. Right, so at this point, I'm going to start putting labels on the different things it talks about. So the sodium sulfite, this is the sample. So let's put a little box, there's the sample, and we have 0.72 grams of it. The solution is made up to 100. So this is the part I was saying where it's made into a standard solution. So standard solutions are made up in these things called volumetric flasks, which you probably see them in the lab. It's a round bottom flask with a really thin spine. And then on the side, on the neck of it rather, there's like a line, scraped out, which tells you the exact volume to fill it to make the required amount. So if you've got a volume of 250, you fill it to that line and it's a 250 flask. In this particular case, it's a 100 centimeter cube flask. And the reason why we need to do this is so we can actually conduct the experiment, the titration, and repeat it. Okay, so the student dissolves 0.72 grams of the sulfate in water. The solution is made up to 100. So this is our standard solution of the sample. The student titrates 25 of the solution. So they take 25 centimeter cubed of this and they put it into a flask and they titrate it against potassium manganate. So in the burette, we have KMnO4. And it says the volume of KMnO4 required to reach the endpoint is 26.2. So we know that the concentration of it is 0.02 moles per dm cubed. And we know the volume used in the reaction is 26.2 centimeter cubed. Before we jump into the calculation, let's put some labels on to make sure you understand this. So the sample, let's call that number 1, is reacting with the oxidizing agent, which we'll call number 2. Where is this reaction taking place? It is taking place in this flask. So 1 plus 2 equals a redox reaction. What is the equation for this reaction? It is given to us there. It's that one. Okay, so that's the reaction taking place in the flask. And to go back to what I was saying at the beginning of the video, we want information about the sample on the left. So this is where we started, and this is the finish, if you like. But to get information about the sample at the start, we literally have to work backwards, back to the start. So that's where the name back titration comes from, or loosely referred to as just a redox titration in this case, because the redox reaction is taking place. I have to start at the end. So the first thing I'm going to do is I need to work out the moles of the manganate that is reacted. Number 1, moles equals C times V. So moles is concentration times volume. So it'll be 0.02 times the volume must be turned into centimeter cubed. So 26.2 centimeter cubed is 0.0262 decimeter cubed. And times that by 0.2 gives us, so that's the number of moles of manganate that has reacted in the conical flask with the sample. Okay, so now the next thing we need to do is we need to work out how much sulfite is reacted. So to do that, we do the molar ratio of the potassium manganate to the sulfite reacting. So you can see 2 lots of this reacts with 5 lots of that. So if I want the moles of SO32-, I've got to apply this 2:5 ratio. So to get the moles of sulfite, I need to divide it by 2 and then times it by 5. 5.24 times 10 to the minus 4 divided by 2 equals, then times it by 5 equals an answer of, just put in brackets here what I just did, I divided by 2, then I times by 5 because it's a 2:5 ratio. Okay, so that's the moles of SO32- that is reacted in the flask. But remember what I said, we've got to work backwards. We've got to get the moles that's in the sample. So we have to go back to that location first, which is the standard solution contained in the sample, and then back to the sample at the beginning. You can see in the titration 25 centimeter cubed of the SO3 2- has been used in the reaction. And that has come from a bigger pot of 100. So therefore, to get the moles, let's write this next. So the moles of SO3 2- in the SS, the standard solution, all I have to do is just times it by 4, because this 4 times is coming from 4 times as much. So timesing that by 4 gives us, so that's the moles of SO3 2- in the standard solution. So we know the moles there, but what is the moles going to be there? Well, the answer is it's exactly the same. So why is that? The reason why, so let me just annotate this. So the moles is the same going back from the flask to the sample. The reason why is because what you've done, you've taken this solid sample, you've put it into an empty beaker, and you've added water on top of it. Can you see that it's just the same sample, right? The mass of the sample has not changed. You've just dumped water on it and you've dissolved it. It's still, the same mass of the sample. So number 4, moles in the sample, is also 5.24 times 10 to the minus 3, which means there is just one step left. So let's go back to the question. Determine the percentage purity of the sample of sodium sulfite. Well, we are told that the total sample has a mass of 0.72 and that the moles that is actually reacted is 5.24 times 10 to the minus 3. Now I need to turn that into a mass to find out how much that has actually reacted. So now I'm going to use the solids formula. So mass equals moles times RFM. So the moles is 5.24 times 10 to the minus 3 times the RFM of sodium sulfite. The RFM of sodium sulfite is going to be obviously greater than just the sulfite ion. So why am I allowed to use the same moles for just the sulfite ion as the sodium sulfite? And the answer is there's a 1-to-1 ratio between them two. So 1 mole of this produces 1 of that. So the moles will be the same, but the RFM will be different. And remember, the question is asking, if I just underline the bit we want here, determine the percentage purity of this sodium sulfate. So we have to use the RFM of this and not just that. So let's go ahead and do that. 23 plus another 23, because there's 2 sodiums, plus 32 plus 3 times 16 is 48. So Na2SO3 gives us a total of, or to 2 decimal place, 0.66 grams. Number 6, I'll do this in blue, is the last point. We have to determine the percentage purity. So the percentage purity, this is the easy bit, the last bit, is the mass reacted divided by the total mass times 100%. So the mass that's reacted, where we just determined, is 0.66. The total mass of the sample was given to us as 0.72, which is that there. So now we do 0.66 divided 0.72 times 100, and this gives me an answer of, so to 2 significant figures, about 92%. There were 6 steps in that calculation, and that is very common for these questions. They're always 5 or 6 markers, and they always involve the same steps, which is determination of the concentration of the oxidizing agent or acid or base in the burette. Number 2, your molar ratio, to find the moles of the sample reacted. Number 3, scaling back to the moles in the standard solution. And then number 4, 5, and 6 would be conversion into the mass, and then percentage purity, or if it was a concentration, you'd be using the mole CV formula again. Right, I hope that was helpful. If you have any questions or are stuck, please comment down below and I will help you. But go and look at the next videos on this topic. I've done several covering these different redox titrations and the different sort of flavors you could be asked. And I'll see you in the next one.